Okay, welcome to lecture 10.8. This one, I think I can do this hopefully 15 or 20 minutes. Just give a little bit of the rudiments of my paper with Crable. The one, gosh, I can't even remember the title. Something like Rubber Checks, Golden Parachutes. The idea is that Crable and I looked at um, this year 19, I think it's 1992, when a lot of incumbents in the House of Representatives had retired. And it was kind of a mystery why so many had retired. And some people were saying, well, part of it was redistricting. They knew they'd lose if they ran. There was this House bank scandal. They had this house bank where they basically had free overdraft protection, and House members were using that free overdraft protection basically as a way to get interest-free loans. They would just write a bad check, not pay it for a long time, and you didn't have to pay interest on that bounce check. And then and then there was a third case. There was this crazy law that it used to be the case if you're a House member. I think it used to be that case in the Senate even, that if you had this campaign war chest, so you'd been raising money in previous elections, you didn't use all the money, you could, save that money for a future election. Okay, they called that your campaign war chest, and they had this crazy rule that if you retired, you could convert that campaign money to personal money. You could just pocket it. Whoa, whoa, whoa! That's violating the spirit of the campaign law. Um, Now they got rid of that law, but the House grandfathered in when they got rid of the law. They said, okay, the law will no longer be in effect in at this date in 6 months or whatever. But everyone who's a current member is grandfathered in. And you get to use the old law, which means you still get to convert your campaign war chest to cash. They had that law, but then eventually they said, no, that looks bad. Even that we have to end the grandfather status. So even the people who are grandfathered can no longer have the old law. And they said, and I think it was 90. Gosh, I think it was 92 would be the last year you could do that. I can't even remember the dates of it. So all of a sudden you had this case where all of these incumbents who are grandfathered realize, oh, this is my last year. I can convert my campaign war chest to cash. But to do that, I got to retire this year. And maybe a lot of people were retiring because of that special law. So there's a lot of factors in this one year. I think it was 1992. I think I got that right. When they all retired. So we're going to use that. And then in the end, we're going to do things like estimate counterfactuals, like how many fewer retirements would you have seen if you didn't have that law? How many fewer retirements would you have seen if you didn't have redistricting? How many fewer retirements would you have seen if you didn't have that House bank scandal? Um, and then because we have a structural model, we're going to put in your decision to retire or not is based on the probability that you would have won. Okay, then we can do things like have all these other counterfactuals. What if every member of the House had been guaranteed, all those incumbents had been guaranteed they'd win if they chose to run for reelection? If instead that had been the case, how many fewer retirements would you have? And so we call that strategic retirements. It's when you retire because you see that you're going to lose. So we can estimate a number to say how many of the retirements could be called strategic retirements, and we get that from running that counterfactual, like what if instead everyone had been guaranteed reelection? All right, so we do things like that in the paper. Um, all of this is related to Feinstein's it's a special version of Feinstein's detection controlled estimation. And when Feinstein does this, he has a two-step process where first a person makes a decision or an estimate, like whether he's going to run for re-election or not. And then, if he does run for re-election, uh, um, first he decides whether he would win re-election if he ran, and then if he does, and given that estimate, he decides whether to retire or not. And you can have similar things in a lot of different things. So, like a criminal, or not even a criminal, a potential criminal. So, and I think Feinstein analyzes potential tax cheats. So, I can cheat on my taxes or not, but before I do that, I might want to estimate, am I going to be caught or not if I do cheat on my taxes? And so then I calculate, from my independent variables, how much money I make, how much the IRS wants to audit me. There's different independent variables that will help estimate that, predict that probability. Given that, my probability of being caught, that impacts my decision whether to cheat or not. And then in the end, I decide whether to cheat or not. The great thing about Feinstein's model is it allows us to calculate all these counterfactuals. So I can estimate how many extra people would the IRS catch if they audited everyone, okay? If instead IRS audited everyone, how many fewer people would cheat if they knew that? So that's the great thing about these models is that once you get all the estimates, you can run all these counterfactuals. You can estimate things that didn't happen. How many fewer people would have cheated if the IRS audited everyone. You can do it with some other weird things. So I had a student once. I don't know if she followed through on it, but she did it for a presentation. She had data on airline flights. And he said, okay, an airline flight, say there's some bad weather, the airline decides whether to cancel the flight or not, okay? She put in her model to say, like, well, what's the probability of a crash given that we take off? What's the probability that it's a safe flight given that we take off? That probability term is in her model. So that's in the airline's calculation of whether to allow that flight to take off or not. Once you do that, once you have all your data and you have all those probability terms, the probability that the flight would have crashed, you can do things like say, okay, of all the flights that didn't take off, what's the probability that of each of them, that each of those cases would have had a crash? And so you can estimate that the expected number of crashes that would have happened if all those flights would have taken off. So it's some crazy things. It's almost like magic, some things you can estimate from this detection control estimation. And it's a very useful tool. I think you can get some very interesting papers out of this, and I encourage lots of you to try to think of I think it's a great area to try to apply these models to one of your own research projects, and I think you get at least potentially a very interesting paper, and it's partly because of your ability to estimate these counterfactuals. Okay, I've already talked a long time about just motivating the paper. Let me talk the rudiments of Mein Crable's paper. Okay, first of all, so our level of observation, it's only 1 year's worth of data, and so we looked at all the members of the House, and so there's 435 of them, but we threw out. There was a few cases where someone had died. Okay, so and then there was another few cases where they decided to run for the Senate, and I thought that's too complicated. We're just going to omit those cases. So there's something like 12 cases. I think maybe it's 20, something like that, where someone either died or decided to run for the Senate. So our remaining cases is something like 420. Okay, so I goes from 1 to 420. Okay, for each person, we're going to assume or define BI equals the benefits of so each person is going to decide whether to run for re-election or not. So BI equals the benefits of office. I'm going to say winning if you decide to run. Okay. Now, PI equals probability of winning given I runs. So I does not retire. Okay. And then CI equals cost of running. And then we assume our model is that I runs if and only if BI times PI. So your expected benefits of winning, if that is greater than CI. Okay. All right. Now, next thing. BI. BI equals XI times beta. Okay, so XI is some independent variables, beta's the parameter, and then CI equals YI times gamma, and then we're going to add an error term to this, plus UI. And we're going to try various distributions, but the key one is that UI distributed normal 0 sigma squared U, because we're going to have another random variable that we're going to throw in here. So all right, that's our model. Okay, but now also we're going to assume okay, given I runs, I wins if and only if ZI delta minus VI is greater than 0, where VI is a random variable, and we'll have various distributions, but the key one is that it's distributed 0 sigma sub V squared. Okay. So now, all right, we've gotten this. So now, that's the structure. Now we can say the probability, this PI, the probability that I wins if he or she runs, and it's just this, the probability that that is greater than 0, and that is probability VI is less than ZI delta. Let's divide both sides by sigma V. That equals probability VI divided by sigma V is less than ZI delta divided by sigma V. VI divided by sigma V, given our assumptions, that's a standard normal random variable. Okay, so given that, if it's a standard normal random variable, that probability just equals big phi of this stuff. ZI delta divided by sigma V. Okay. Turns out we are going to have the usual identification problem. This is going to be, it's like a probit. That's where we're going. If we multiply sigma V by a constant and delta as a vector of parameters, we multiply all the deltas by a constant, multiply sigma V by the same constant, that probability term is not going to change. So we have an identification problem where we do set sigma V equal to 1. Okay, so given that, we have Pi equals phi, big phi of ZI delta. Okay, so we've already made some headway. Okay, so remember, I runs if and only if Bi times Pi is greater than Ci. Bi equals this, Ci equals this, Pi equals that. Okay, given that, all right, we can rewrite this thing. Okay, we can say I runs if and only if Bi, Pi, I'm going to say minus Ci is greater than 0. Bi equals Xi beta. Pi equals phi of Zi delta. Ci is Yi gamma minus Vi, it's all greater than 0. So I runs if and only if, I'm going to put that VI over here, if and only if VI is less than all of this stuff. So that means probability I runs equals probability VI is less than Xi beta times phi Zi delta minus Yi gamma. Okay, now Vi is distributed normal, 0, sigma sub V squared. So the standard deviation of Vi is sigma sub V. So all I'm going to do is I'm going to divide by sigma V. All that by sigma V. Right, now this is a standard normal random variable. Okay, so now that probability just equals big phi of this stuff. And that equals Xi beta phi of Zi delta minus Yi gamma, all divided by sigma V. We've got another identification problem. If we multiply all the betas, you pick some constant, multiply all the betas by that constant, multiply all the gammas by that constant, multiply sigma V by that constant, this probability term is not going to change. So what we're going to do, we're going to set sigma V equal to 1. So now we've got it. Probability I runs is just this term, big phi of Xi beta times another big phi term. So we got a big phi within a big phi term within a big phi term. Okay. Otherwise, this is just, that's my old professor, that colorful guy. So it's just a rat shit probe it if you don't have that phi term. Okay. But we put that in. The structure says put that in like that. And it's not quite a rat shit probe it, but it looks very similar to it. Okay. So what we have is I runs, if and only if the probability that person I runs is this term. Probability that he or she does not run is 1 minus that. Our dependent variable is just with each person I, each incumbent I, whether that person runs or not. We have a recipe, okay? Our dependent variable is 1 or 0, whether person I runs or not, okay? And we just use the probability that person I runs is this. Probably person I does not run is 1 minus that, okay? We've got it. We've done our recipe. We can now write, it's very easy to write a likelihood function, okay? It's just going to be L equals big pi, I equals 1 to, I think it's like 422 cases of people who didn't die, didn't run for Senate. And then you have big phi of that, xi beta phi zi delta minus yi gamma. And that is all raised to the, I can't remember, let's see, what's a, I don't remember what I used in the paper, but we're going to call, let's make our dependent variable, unfortunately, run and retire both begin with the same letter, okay? Let's call r sub I, our dependent variable, whether I runs or not. So that equals 0 or 1, whether he or she runs. So raise that to the ri power, that's 1 or 0, and then multiply it times 1 minus phi, big phi of all that stuff, raised to the 1 minus ri power. That's the likelihood function. Okay, so that's it. So you just plug it into R. I think I used SAS. So we said, estimate beta, delta, gamma from that likelihood function. Okay, once you got it, then you can start saying things like, with each person I, what's the predicted probability that he or she will run? Okay, now I'm going to give you, I'm not going to call it a homework problem. I'm going to call it optional or optional additional problems, something like that. Okay, so if you knew beta hat, gamma hat, delta hat, with each I, they're independent variables, you could say what's the probability that person runs. What would be the probability that I runs if he were guaranteed re-election? So all you got to do is just, in all those cases, or in this case, just where we have phi of zi delta, put a 1. Okay? Phi of that is the probability that I runs if he or she were guaranteed re-election. It's just set that phi of zi delta equal to 1. So here's a case. If we had the counterfactual, what if we had this imaginary case where everyone was guaranteed re-election? What would be the probability everyone would run? Okay, sum that up over all the I's. That gives you the expected number of people who would run under that counterfactual scenario. Compare that to the actual number who would run, and you can say, like, how many more people would have run if they could have been guaranteed re-election? Suppose I retired, the person I retired, but suppose instead he had been forced to run for re-election. What is the probability that he or she would have won? So all you got to do is look for that case. Say person 37 in your data set. And then all you gotta do is just look at person 37's z terms, his person 37's independent variables. You've got your estimate of delta, and you can say phi of z37 times delta, compute the phi of that. That's the probability that that person would have won if he or she had run. And so you can do things like saying, of those people who didn't run, how many of them actually would have won if you'd forced all of them to run? Another counterfactual that you can run. Okay, so that is problem 3. I might add another problem or two. Probably not. Probably just stick to that. There's no graded homework, so you have no assignment. So these are just suggested problems. You might want to do it your own. My suggestion: read them over. Read the paper that I wrote with Crable. You've seen my introduction of the paper. Now I think you're capable of reading the paper pretty easily. Read the paper. Think about how you would solve those homework problems if another counterfactual. If I had assigned you actual homework to do. Okay, so that is it. That's the final part of session 10. Okay, see you next week when I'm going to go more in detail over that my paper with Crable. But I wanted you to see this part and start thinking. I think there's a lot of topics you have in your mind that may be related to mine and Crable's paper, which is a special case of the Feinstein detection control estimation. There's lots and lots of problems out there, I think. So I told you one about a former student who looked about whether a plane takes off or not. And this is along the way, you can estimate the probability that that plane would have crashed if it would have taken off. Let me give another example. One of my current students, as I speak now, Harry Pan, is looking at, and we're writing in this paper together, he is looking at movie censorship in China. And so there's anecdotes about whether the Chinese government has banned a movie, an American movie or not. But it's more difficult than that, because just because an American movie is not shown in China doesn't mean that the government censored it. A lot of cases, the movie just wouldn't have made any money. And so no distributor in China would want to show it, would want to buy the rights, because it just wouldn't be profitable. And so what happens is, it's kind of like this case where there's a two-step process. So every every potential distributor says, what's the probability that this movie would actually be profitable? Given that, I'm going to decide whether to buy the rights or not. And then involved in that is also the probability that the Chinese government would have banned it or not. And so in the end, we have this let me say, the early versions of the paper, we were going to have this dependent variable, just whether an American movie is shown in China or not. And whether it's shown is first the probability that it would actually make money times the probability that the government is not going to ban it. So it's not quite like a probit, but it's kind of similar to this model I did with Crable. So it's one of these two-step models that it's very similar to Feinstein's detection controlled estimation model. And so I think there may be lots and lots of topics that you may be thinking of that would be similar to Feinstein's model, that you might want to use this technology to do research on your own topic that you may think of. Okay, so I wanted you to see a taste of that while you're thinking of presentations you're going to do for the class. I wanted you to see at least a taste of what the Grosclose-Crable model would be like, but next week we'll go into more detail of that. And I encourage you, I think there may be some low-hanging fruit out there of ways to apply that model to some of your own research topics. Okay, I'll end there and see you next week when I talk more about my model with Crable. Okay, see you then.